The AIrTonomy team at Purdue University is developing research infrastructure for autonomous aerial vehicles, focusing on safe and trustworthy artificial intelligence and machine learning deployed in challenging environments. Join us September 11th through 12th to qualify as a lead user with 6 months free infrastructure use. This infrastructure will support an unsurpassed variety of operating scenarios, including single vehicle and swarm operation, and beyond visual line of sight corridors, urban areas, forested areas, and rural areas. These environments will be within a contiguous 15-mile-long corridor, where transition between them may also be studied. Vehicles will be carefully instrumented for ground truth using a combination of RTK GPS, onboard inertial sensors, and indoor-outdoor motion capture cameras. Interaction with human operators will also be carefully instrumented for studying human autonomy teaming. The key physical infrastructure of AIrTonomy is what we call the Purdue Unmanned Aerial Proving Ground, or PUP for short. Geographically organized within a triangle near Purdue University, it brings together unique indoor and outdoor facilities and infrastructure components that ensure that research can move back and forth from lab to life. While each physical component on its own offers unique capabilities for research, the major value comes from the integrative use of multiple components jointly. To ensure integration into real urban airspaces and allow vehicles to fly within PUP, we will work closely with our partner Saab to install ground communication and networking infrastructure for urban airspace management. What we call the Purdue XTM system will produce air traffic and airspace data of high value to our research community. One key element of Purdue XTM is an active R1410 X-band radar. Combined with 3 passive radars placed outside of PUP, we can identify small UAVs flying at low altitude within the airspace. In addition to these radars, we will also establish a low-altitude weather network, a distributed and mesh network of low-cost weather sensors that provide accurate low-altitude aviation meteorological data not delivered by other sources, and remote ID solutions that support the new FAA regulatory requirements for AAVs. We will now take a look at the AIrTonomy infrastructure at Purdue Airport. Constructed in 2019, the Purdue UAS Research and Test Facility, PERT, is the largest indoor motion capture facility in the world. PERT is half the size of a football field with millimeter accuracy, allowing us to capture highly granular data about a vehicle's position and attitude in real time. The motion capture system relies on passive reflective or active LED markers on vehicles to measure their position. The facility is equipped with 60 motion capture cameras with up to 1100 frames per second data rate and with camera-to-vehicle latency of 25 milliseconds. This technology enables mixed reality testing and detailed sensor emulation. For example, the degradation of GPS while flying through an urban canyon or forest can be emulated by computing line of sight to GPS satellites, given 3D building models. In addition, we can render virtual camera views and sensors such as radar and LiDAR using our mixed sense infrastructure. Lessons learned at PERT can then be demonstrated in the outdoor facilities that we are creating as part of AIrTonomy. The Smart Operations Center, SOC, is the most immersive and connected tactical command center and will transform the future remote operations and urban airspace management. The highly reconfigurable space will enable teams of different sizes to perform tactical operations related to missions of various complexity, for example, multiple AAVs, swarm operations, etc., and beyond visual line of sight. It will be equipped with a gridded wall of screens along with motion capture cameras, similar to PERT, and VR/AR technologies to allow for truly immersive and interactive outer spaces. Researchers can use state-of-the-art wearable devices such as high-performing eye tracking devices, mobile EEG devices, and heart rate sensors. To move from lab to life, we will build PUC, the Purdue Urban Canyon Lab, that will make use of a 12-acre field within the Purdue Martell Forest. Similar to PERT, it will make use of motion capture cameras that use active LED markers to capture vehicles' position at centimeter level accuracy. At Puck, we will construct urban canyons using temporary or minimally invasive buildings and leverage the existing digital forestry infrastructure at Martell Forest to study vehicle operation when signal degradation of GPS, radar, cameras, and communication networks such as 5G prohibit nominal operation. In Puck, researchers can perform flights at low altitude and extended and beyond visual line of sight or within or near buildings. We envision such futuristic applications such as deploying a swarm of surveillance drones from a large fixed-wing drone flown from a nearby airfield. To support larger fixed-wing unmanned aerial vehicles as part of PUP, we're building a dedicated runway, the Pup Airfield. This will allow people to perform research related to takeoff and landing with larger UAVs, the integration of multiple disciplinary UAV types into a cohesive operating environment, and understanding UAV integration into a wider airspace picture. The airfield will have a runway of 1,200 feet by 130 feet, hangarage for multiple UAVs, office and operation spaces, and will be registered as an airfield with the FAA and displayed on air charts. Drones with larger payload and range capabilities are essential for future urban air mobility. Scenarios such as firefighting, forestry, inventory management, and cargo delivery for the middle mile all represent use cases where this type of vehicle can excel. At Purdue, we own and operate 2 mid-scale UAVs with a wingspan of 31 feet, a maximum takeoff mass of 1,000 plus pounds, and a range of 600 plus miles. As large fixed-wing drones, they have a takeoff and landing requirement more closely aligned to traditional manned aviation and will operate from the PUP main runway. These aircraft are designed to run a flexible payload bay, allowing researchers up to 300 pounds and 185 gallon of capacity to install and test sensing payloads. This exceptional payload ability unblocks several limitations that existing UAVs pose and can carry sensors that previously only manned aircraft could accommodate. Both the airfield and the vehicles operating out of Pup Airfield will be equipped with a sensing infrastructure that would allow us to collect ground truth data and emulate virtual sensors or mixed reality in real time. We will combine an RTK-based ground station with vehicle onboard IMU sensors to perform sensor fusion. At the same time, portable motion capture cameras allow researchers to collect ground truth data where needed, for example, during landing. Researchers both at Purdue and other research institutes will have access to our fleet of UAVs, from larger fixed-wing vertical takeoff and landing aircraft, as well as smaller multi-rotor platforms. We envision PUP forming the anchor point of a UAS Smart Crossways corridor across Indiana. The 600-mile operating range of our vehicles, we can navigate this corridor and land at partner sites, complementary proving grounds for research on AAVs. In addition, we also plan to build a smart Crossways corridor to move things and people from Purdue to Indianapolis. Translating lab to life related to long-range flights beyond visual line of sight, we will make impact to the state and nation at scale. Once built, the AIrTonomy infrastructure will allow the U.S. to lead the discovery of the next generation of autonomous aerial vehicles so that these systems may be trusted to conduct missions such as search and rescue, firefighting, and law enforcement in a wide variety of environments where operations are challenged today. Thank you for watching, and we hope that you will attend our workshop on September 11th and 12th at Purdue University or watch our online webinar. Please scan the QR code for more information.